Hello all, welcome to Excel Academy. So today we are going to start with the new module, that is your module number 5, that is Z transform. And in the case of Z transform you have that is the problems on Z transform, the basics of Z transform, as well as the properties of ROC, right? ROC stands for region of convergence, right? So now coming on to the Z transform, so we are going to divide this into three sections. One is the Z transform introduction, one is the small derivation with respect to Z transform, and other one is the properties of region of convergence and what is the region of convergence, right? So now very first let us learn about Z transform, right? See, very first let us learn about the Z transform. So we have one question that arises. So what is Z transform, right? So what is Z transform? So Z transform is very first point. A Z transform is what I can say, the extension of discrete time Fourier transform, right? So I'll write the Z transform is the Z transform is what? It is the extension of the discrete time Fourier transform. Extension in the sense like it is somewhat advanced of that particular DTFT, right? Extension of DTFT. I guess you got what is DTFT, right? DTFT stands for discrete time Fourier transform. So this is what is the first point. So now coming on to my second point. So what my second point says is that so you can apply this particular Z transform. So here we learn about the application of Z transform. What is application of Z transform? So you are going to apply the Z transform to wider range of signals, right? Just a second, I'm writing it, guys. So I'll write along with I'll tell, so it might take some time. So application of Z transform is what? Sir, application of Z transform is for wider range of signals, right? Here I'll continue this. So it is for wider range of signals. Why wider range of signals? It is because I'm going to showcase that also. See, so just a second, I'll take another one. Yes. So see, it is applied for, just a second guys, I'm really sorry. Yes. So it is applied for wider range of signals, right? Why wider range of signal it is applied? As because in the case of your DTFT, so what is that happen? Many signal don't converge in the case of DTFT. So in the case of what I can say, your Z transform, the signals will converge, right? So that is why you can also tell that there are many signals for which DTFT will not converge, right? There are so many signals like this for which your DTFT, that is discrete time Fourier transform, will not converge, right? It will not converge, and so therefore what I can say, I can say that for those signals here, what I can say here, Z transform will converge, right? Z transform will converge for those particular signals. So please do understand, very first point what we learned was that it is an extension of discrete time Fourier transform. What is the extension? In the sense it is like somewhat advanced of the discrete time Fourier transform. And why we are using this? So we also told that we are using it for the wider range of signal. The application is for wider range of signal. This is also important, right? Yes. Why wider range of signal we are applying it over here is because you know that for some of the signals, that is there are many signals for which the DTFT will not converge. Converge is what I can say, it is meeting up at a point, right? So for converge, it doesn't converge, wherein you are, what I can say, your Z transform will converge, right? Wherein a Z transform will converge. So therefore you can see that it is the, what I can say, your Z transform is advanced concept of discrete time Fourier transform, right? I guess you got to know by this only, right? Yes. So now coming on to the next one, that is the proper definition of Z transform. So see here, Z transform will converge, right? I told you DTFT will not converge for many of the signals, so therefore the Z transform will converge, right? Yes. So now coming on to what I can say, the next one. What is the next one? That is the definition of Z transform. So we learn the next thing, that is definition of Z transform. I'm sorry, definition of Z transform. So what is the actual definition of Z transform, right? So my actual definition of Z transform is that, so it is the one wherein it will convert. So here conversion takes place and it will convert what? It will convert the discrete time sequence, right? So what is discrete time sequence? That is x of n, right? You got it right. It is discrete time sequence, that is your x of n, right? See, it is x of n. So it is consisting of what? Real and complex, that is what I can say, numbers, right? It is consisting. So please do read it, understand. I'll read it once again. So it is it will convert discrete time sequence, that is what a discrete time sequence is what? That is your x of n. So this is really important, and it is consisting of what? It is consisting of the real and complex numbers. So it will convert that into what? It will convert that into what? Convert that into frequency domain representation. What it will do? It will convert that into what I can say, the frequency domain representation, right? Yes. So it will convert that into frequency domain representation, right? Representation. And then this is what is the definition for the Z transform, right? So this is what is for the Z transform introduction. So what did we learn in the introduction of Z transform? So in the introduction of Z transform, we learned that Z transform is an extension of what? That is discrete time Fourier transform. And next, what did we learn? We learned that this Z transform can be applied to wider signals, that is wider range of signals. Why we have to apply for the wider range of signal is because in the case of a discrete time Fourier transform, many signals are present wherein discrete time Fourier transform will not converge. So for those signals, a discrete time Fourier transform will not converge. So for those signals, that is the Z transform will converge. So therefore that is why we are making use for all the signals, that is wider classes of signals, because here see in the DTFT you can see that there are many signals wherein DTFT don't converge. So that is why if we make use of Z transform, so then what is that going to happen is, there are all the signals that don't get converged by the DTFT, it will get converged by Z transform, right? That is what is the one. And then we learned about the definition of Z transform. So what is the definition of Z transform? The definition of Z transform says that it will convert what? Discrete time sequence. So what is a discrete time sequence? A discrete time sequence is what I can say, this x of n. So this x of n, so it consists of real and complex numbers, so that it will convert into what? Frequency domain representation. So this is what is for the very small introduction of Z transform. And next video we are going to learn about the Z transform derivation, right? Yes. So what I'll do is I'll leave it part by part. So first, this is the introductory part. So I'll leave this as a one video. Then I'll leave the Z transform derivation as another video. And then I'll leave the properties of ROC. That is what is region of convergence and properties of region of convergence in another video, so that you can get to know all the things clearly. Thank you.